So I'll share my screen. All right. So today's lecture is a little bit shorter because we're coming back to the Lsd formula. As I told you in QFT1, we need to understand the Lsd formula also. To understand better the Lsd formula, we need to understand loops and renormalization, and that's what we'll do now. So, so what was the Lsd formula? Well, there was a formula that related the correlation functions to the S matrices. S matrices being product of in and out states, or equivalently the element, the matrix elements of S. All right. So the crucial element that we could not understand well in QFT1 was the renormalization factor Z. So as we saw, we defined a factor Z that is the wave function renormalization, meaning the thing that multiplies the p-squared part of the kinetic term. But that in turn comes from the two-point function. So really, that means that we can think of the Z factor as coming from the quantum two-point function in the following way. So we have the two-point function. We have the two-point correlation function in the true vacuum of the theory, and we make a Fourier transform to momentum. But when we do this, the momentum is arbitrary. However, let's go to near the pole, near near the neuron shell, so where p squared goes to minus m squared. Then formally we can say that the dependence near the pole is this factor minus iz divided by so times the free propagator, so 1 over p squared plus m squared minus I epsilon. All right. So so that's the formal definition of Z. So it's really near the pole, divide the full propagator with the free propagator. And therefore, this is related to, since this has a p squared part, this is related to the Z factor wave function renormalization in the Lagrangian. Now, to obtain the Lsd formula, what we'll do is we'll take an inductive point of view. So we'll consider a single momentum. That is to say, we'll take one Fourier transform only one over only one of the coordinates of the phis, and then at the end we'll see that will relate to. So if this is an n-point function, will relate to an n-1 point function. And since at 2 points we already found by definition this result, this will be true for all n's. All right, so let's take the Fourier transform over x, one of the coordinates in here, and moreover, x is the spatial x and the time like x0, and x0. Let's split it into into three parts: a t plus going to plus infinity, t minus going to t plus, a t minus infinity going to t minus. And we'll call these respectively region 1, region 2, and region 3. Now, the first thing to observe is that region 2 will be ignored because we're looking at the behavior near a pole where this thing is diverging, right? It's going to infinity. So that means that finite terms will be ignored, and the integrand of the integrand, the correlation function is analytic in P0, and then this interval is also finite. So that means finally this region 2 is a finite contribution that will be ignored. Therefore, we'll consider only regions 1 and 3, which will be diverging. Let's start with region 1. And so I've taken a Fourier transform of one of the coordinates, and I called it one of them. I called the one Fourier transform x, and the other is z. But of course, when we do this, we have to make a choice, and the choice that we make is that x over which I Fourier transform is such that x0, its time component, is the largest time among all the coordinates. That is to say, all the z zeros, zi zeros, are less than well. So that also implies we're also choosing t plus and t minus in a certain way, not arbitrary, but such that all the zi zeros are less than t plus. And since we're in the region 1, it's also less than x0. That means to say, for all the integration region of x0, it happens that x0 is the largest. All right. If that is the case, then since the symbol t is time ordering to the left the largest time, that means I can just pull it outside of the t operator, of the time ordering operator, and then I can insert the identity on the right of phi of x. The identity expanded over a complete set of states that I'll call lambda q with momentum q. And this is a sum, but in particular for momentum means an integral of a momentum, and the sum of the corresponding lambdas, which means other kind of variable than q. And of course, for relativistic invariance, I have to have 1/2 eq of lambda. All right. So when we do this, we insert, as I said, to the right of phi of x, and therefore also to the left of the t operator, this lambda q, And then I have this integration factor. Okay. So we obtain this element, this matrix element, the total vacuum, phi of x, lambda q. And first of all, this is a Heisenberg operator, so I can write it with a translation operator this way: e to minus ipx, phi of 0, e to the plus ipx. And then the momentum operator acting on vacuum gives nothing, so I can just ignore this. But the momentum operator acting on lambda q gives q, the momentum q. So here I obtain the number e to the plus I qx, where q0 is still eq. And the remaining matrix element is now at 0. Then we have the integral over spatial x. And I have this e to the minus ipx. And from this, I have e to the plus iqx. Therefore, I have e to, so let's emphasize, I have this, and I have this. So these together give the integral over special x of q minus p, which is 2 pi cubed delta of p minus q. All right. If I have this delta, then I can do the integral over q. So I can do this as well. Which of course replaces everywhere q with p and eq with ep. And as you remember from QFT1, you have to also introduce a regularizing factor, e to the minus epsilon x0, in the usual manner, in order for the full integral to be finite. So then we're left with what? Well, I have this integral over x0. I still have sorry, where was that? Yeah, from here. Yeah, so I still, yeah, here I should have said there's x0 and I cannot draw. Anyway, and x vector. So x vector was taken care of, but we're still left with x0. So I have e to the I plus I p0 x0 from here, and e to the minus I q0 x0 from here. But at q0 is eq equal to ep, that means this is actually 0. But moreover, we've introduced this regularizing factor, so the only thing that that remains is oh, sorry, no, p0 is still arbitrary. I'm sorry. It's just q0 is equal to ep, and then we still have the regularizing factor. So the in the integral over x0, we have p0 minus ep plus I epsilon, which gives the regularizing factor. And this is integrated from t plus to infinity. So this integral is the same exponent. divided by this bracket in between plus infinity and t plus. The reason for I times I epsilon means e to the minus epsilon times x0 is that the contribution at infinity is 0. So we're left with the contribution at t plus, which is minus the exponent divided by this denominator.
So I have a question.
Yeah.
Can I do everything in Euclidean and then get this regularizing factor without putting it by hand? Because here we are putting it by hand.
You remember that we're doing the Lsd formalism, which means that we have to define a relation between correlation factors and S matrices. And S matrices are by definition in Minkowski space. You cannot define S matrices in Euclidean space because you don't have time, you don't have propagation, right? So you cannot do this in Euclidean space now.
So the only way to get the I epsilon is putting by hand? No.
Yeah.
No,
the way we did it at the beginning in, before doing the Euclidean treatment in QFT1.
Okay.
All right. All right. So what is left? Let's see. So yeah, we have the sum over lambda, and then we have this propagator thingy, and then we still have had the 1/2 epsilon, 1/2 EQ of lambda, but Q was replaced with P, so minus 2 EP of lambda. And then the matrix element at 0 and the lower n correlation function. But what's the denominator? So remember, we're looking near the pole. So we're looking near P0 going to EP. So P squared plus M squared going to 0 means P0 going to EP, right? EP is square root of P vector squared plus M squared. So in that case, this 2EP can be rewritten as also, so it's approximately equal to P0 plus EP, because P0 is approximately EP. But then multiplied with this gives P squared plus M squared, now this 4-dimensional P squared plus M squared, right? So the denominator is approximately P squared plus M squared minus I epsilon. All right. And here P0 is approximately equal to EP, so this thing goes away, and the regularizing factor is irrelevant because it multiplies this finite T plus. So I just drop it. So this exponent, you just drop it. So what we're left with is this sum over lambda, this free propagator, this matrix element, that's the important part, and then the n-1, well, the lower n. So let's say by this definition, we started initially with the n+1 point correlation function, and now we're left with this kind of with lambda p here, but n point correlation function. So let's since this is an induction procedure, let's start with the initial step. The initial step was the n+1 equal to 2. That is n equal to 1. So in this case, what we get is this omega phi of 0 lambda p, and then here I get its complex conjugate, lambda p phi of 0 omega. That is this absolute value squared. So the free propagated times this thing, this absolute value squared. All right. But we've just defined initially what that was. We defined initially that this was supposed to be equal to this, right? The momentum, yeah, the 2-point function was supposed to, near the pole, was supposed to be equal to this. So that means that this factor now must be equal to z. All right. So if the absolute value squared of this is equal to z, then this omega phi of 0 lambda p is equal to square root z. So I substitute here in the general n case. I substitute this thing as square root z. Okay. All right. So that means finally we've proven that the n+1 dimensional correlation function with one Fourier transferred coordinate near the pole for that one momentum is equal to the this free correlator times square root z times this correlator, where on the left now I have momentum. Right? I mean, it's lambda p, but you know, if I have something else, it's summed over. So you can think of this as just a momentum. Okay. So now, so we've done this. Note that what we've done what we've done is to replace a phi of x from the left with an action. So we replaced this thing, phi of x from the left inside the time ordering with this p state on the left. Okay, so this is an out state. All right, so now let's do the opposite. Let's consider region 3. That means to say, remember, x0 was a choice, so region 3 now means that, and also the choice of t minus means that, let me say it another way. The phi of z1 up to phi of zn have z10 and z1n in some interval, and I choose that interval such that the interval t plus t minus is bigger, right? So t plus is bigger than this, and t minus is t minus is bigger than all of these, and then t minus is smaller than all of these, right? So if I do so, that means that now in region 3, x0 is the smallest of all of them, right? So now in region 3, x0 is the smallest. So that means that all of z1, so z10 up to zn0 are all larger than t minus. That was the choice. And because it's region 3, it's bigger than x0. All right, but now that again means I can put it outside of the time ordering operator, just to the right, because the time I'm ordering is the smallest is to the right. So I put phi of x to the right, and then continue the steps as before. I insert this identity in between t and phi of x. So I insert this identity here, this ket bra part, and this sum. So I arrive at this. And now, as in region 1, I have to evaluate this kind of matrix element. And again, I say phi of x is shifted by the by the translation operator p. That means it's phi of x is e minus ipx, phi 0, e to the plus ipx. And to the right, p acts on the vacuum, so this factor goes away. But to the left, this actor, this p acts on lambda q, so it turns into q. So so we get this number e to the minus iqx, where again q0 is equal to eq, and we've turned this matrix element into the matrix element with phi of 0. And again, I repeat the same thing as here. The integral over x gives now so the difference is so now the factor in here is e to the minus iq dot x instead of plus. So up here we got e to the plus q iqx. Now we get e to the minus iqx, and again this splits into an x0 and an x vector. Doing the integral over x vector, I get this delta of p plus q now. It's a different sign. So I replace q with minus p everywhere. And eq with ep again. So the x0 integral, the x0 factors is e to the I p0 x0, and then e to the I q0 x0. And the regularizing factor. So what I get in the integral over x0, I get p0 plus ep plus I epsilon. So again, the regularizing factor is chosen such that the integral at minus infinity is 0. Sorry, there's a typo here. So the regularizing factor now must be e to the epsilon x0, because it must be multiplied by minus infinity. So so here must be minus. And indeed, you see, I get 1 over I p0 plus ep minus I epsilon. And let me think a little bit. Well, yeah. Well, okay. So it's a choice. So I said near the pole before. So for the Lsd formula, I said that we're going near the pole. So we're going near where p squared plus m squared equal to 0. But that that implies if so what I really have is, since I Fourier transform into a p, what I really have is a p0 and a p vector, right? So what I really have is I have to find a relation between p0 and p vector. So this is so that relation implies a choice of plus or minus. So p0 equal to plus or minus EP, right? So this is not enough to define the definition. So what we really have in region 3 is the choice p0 going to minus EP, right? So p0 equal to minus EP, in which case, again, I have 1 over 2 EP can be written now as 1 over p0 minus EP, or no, EP minus EP0, EP minus p0. And then still that times that with our new choice, p0 is go to minus EP. So this is our new choice for in region 3 for the pole. I still get the free propagator minus I over p squared plus m squared minus I epsilon. And again, as before, I get this thing, which I've seen that this is square root of z. Right? We've seen that this thing is square root of z. All right. All right. So I replace the matrix element with square root z, and then I have this new endpoint function with in states which are in states which are with minus p vector. But then I can redefine. So remember that our integration in region 3 was yeah, but I wrote it in components, but it's e to the minus I 4-dimensional momentum p dot x, right? But now I redefine 4-dimensional momentum p as equal to minus 4-dimensional momentum k. Then minus p vector becomes plus k vector, but then the Fourier factor becomes e to the plus ikx. Okay, and then here we have k. So the only and note that now we have an ingoing state, right? Now we have k to the right ingoing, and this factor e to the plus ikx in the Fourier transform. So then we can iterate this procedure. So we've shown that this is a n+1 dimensional correlation function with one Fourier transform in the case of region 3 with the plus ikx becomes incoming state. In region 1 with e to the minus ipx becomes outgoing state. But either way, you relate n+1 to n, right? So then doing all the Fourier transforms, and remember, the point is that we're doing states, at least the states are outgoing or ingoing, meaning that they can be separated at infinity, right? That was our physical assumption that we started with when defining QFT and S matrices. So then finally we get the Lsd formula, which I guess I've probably not. No, okay, I wrote it a little bit later. It's written here. So the n plus m, the n plus n dimension point function with m factors with e to the iky for the incoming states, and n terms with the e minus ipx for the outgoing states, and then we get the S matrix. And each one, for each corresponding state, we have this free propagated times square root of z. And yeah, okay. So the next step is to think about how to add wave packets instead of having a single momentum. So we started with just a Fourier transform, meaning that the correlation function was of a given momentum p. And correspondingly to the right, we had a given momentum p for the S matrix. So having a wave packet now, means that we have an integral with a just a moment.
Não, que seria L1 e a soma desses L's com relação aos depósitos à vista que deve ser.
So a wave packet means integrating over the momentum, with a function phi of k. And of course, to go back to the previous case, it means phi of k going to 2 pi cubed delta of k minus p. That is to say, focusing on a single momentum k. So if I have this extra complication, nothing much happens. So I still have the integral now over k with phi of k. So that's the new part. But then I get the same separation, so the same matrix element that becomes square root of z, the same iteration factor with n instead of n plus 1. And then when you are near on shell, you get p squared plus m squared minus I epsilon. Again, but the only new factor is this integral that we started with. And again, yeah, I guess I did yeah, so I defined p tilde equal to p0 and k vector. So the integration for the wave bucket is over k vector, but p0 is still p0. So I define p tilde as p0 k vector. So the pole means now p0 going to e k vector, or p tilde squared plus m squared approximately 0. So this means that p squared plus m squared is p tilde squared plus m squared in the denominator goes to 0 again. So what is the new thing? So you have to think about the fact that we have incoming and outgoing states, which are separable. That means at infinity, we can treat them as independent. So in order to observe that, let's consider the scattering from n particles to 2 particles. Then we consider, then we obtain the same integral as before, with just let's see, so this integral over wave packets, and everything else is the same. So still the identity is lambda q summed over q. and still it's there's a Fourier transform over the xi's, x1, x2. The only new thing is that after the Fourier transform, we'll also introduce this wave packet. But the new factor is, as I said, that still, even with the wave packet, the two outgoing particles can still be separated in the far future, which means that when I have this lambda k, even if I have the wave packet phi of k, I can still separate them, meaning this is equal to, well, k is supposed to be corresponding to k1 and k2, right? And so by where is it? Let's see here. So by the no, not here. Yes, here. So when you do the integral over x, we get a delta function of p plus q, where q was the one in lambda q, and p was the external momentum. So now we have lambda q. Anyway, wanted to do a wavy line here, but you have this from the identity. We have this lambda q, and then from the integration, I replace the q with the external momentum. External momentum now being k. So now I have lambda k. But what this means is that I can separate. So before I did, before the wave packets, I did this momentum by momentum. But now I'm saying even with the wave packet, I can still separate. So we still have lambda q1, lambda q2, and breaking in the matrix element, in this matrix element, breaking into lambda q1, lambda q2, and then the integration gives the previous case. So even with wave packets, just from the physical input, the physical assumption of separability, of having incoming and outgoing states, we obtain the same situation. We obtain, namely, the S matrix, which does contain the incoming and outgoing states. So this S matrix is actually the product of the in and out states with corresponding momenta, right? So when I iterate the procedure, I obtain here P1 up to Pn out, product with Q1, K1 up to Km in, which gives this S matrix. All right, so the Lsd formula now is understood in this way as the product, the relation of the correlation functions, Fourier transformed near the poles as free propagators times square root z times the S matrix. What does it mean now diagrammatically? Diagrammatically, we have to understand what it means from the Feynman diagrams for the S matrix. So how do we obtain the Feynman diagrams for the S matrix from the Feynman diagrams for the correlation functions? Well, we've done that, but now let's understand it a little bit more physically. So the Feynman diagrams for correlation functions are the connected diagrams. And to obtain the Feynman diagrams for S matrix, we have to obtain the operation called amputation. Right? So we have some connected Feynman diagram, and we go from the outside part of any external line. We go in until the largest point where we have a single propagator, and we cut there. Right? So we cut this, and we cut this. Oops. We cut this. And then we're left with the amputated part, right? Which is a 1pi diagram, right? One particle yeah, a 1pi diagram. So so why does that mean? Well, as you can see here, what we have cut, well, we have cut this part, which was actually the full 2-point function, the full 2-point correlation function, right? So we divide it by this. This was the 2-point function, the full 2-point function in momentum space, right? Which is this minus I z divided by p squared plus m squared minus I epsilon, right? And indeed, you see in a Lsd formula from the correlation function in momentum space, I divide by these factors. Now it's z instead of square root z. It's square root z instead of z. We don't divide exactly by the 2-point functions. The point functions near the pole would be z over p squared plus m squared minus I epsilon. But so we put square root z instead of z. But why is that? The reason for that is that the 2-point function has 2 legs, and the point is I I have to think of associating a square root z to each leg. So there's a square root z on this leg, and the square root z on this leg. And we're only dividing with the square root z on this leg. All right. Okay, so that's the physical interpretation of this Lsd formula. All right. Now, this amputation procedure relates diagram in the perturbation expansion of correlation functions to diagrams in the perturbation expansion of S matrices, right? So, correlation function, we've talked about before in QF21, that you write the full connected part, that is the correlation function. Write it as a free propagator minus a free propagator times 1 pi part times free propagator plus the one with 2 1 pi's and so on. And that expansion is written here. So there's this free propagator is called delta here, then minus delta, this thing, the 1 pi 2-point function is called pi j if you want. So delta pi delta, then plus delta pi delta, minus, and so on. And this series, of course, sums up into, if you think of this as a matrix with indices, some indices, 1 plus delta pi inverse times delta. If you think of it as just numbers, you can just write delta over 1 plus delta pi. Now, yeah, sorry, this is I don't think I wanted to say that. I want to say this whole expansion. So delta minus this term is this term plus ... equal to this. And why do I mean it's because the sum of these terms is equal to this. But if this is, as I said, if these are just numbers, this is delta over 1 plus delta pi, right? So I put the delta in the denominator. So I write this as 1 over delta to the minus 1 plus delta to the minus 1 delta pi. That is 1 over delta minus 1 plus pi. Pi I've called it I m squared, and the I left it in the numerator. So it's minus I, then minus I over, this is the inverse propagator, p squared plus m squared, m0 squared, plus, and now this term is m squared. But this is a function of p, of momentum. So this, even though I called it capital M squared, is still a function of p squared. So so you see then that the physical pole, so what we're so we have also a physical pole for the connecting for the connected 2-point function, that is for the full propagator. And that is of the type minus I z, where z is some function, or p squared plus little m squared that's different than, a priori different than m0 squared or capital M, or that plus capital M squared. Why is that? Well, sorry, so near the physical pole, near where this blows up, is this plus a finite part. So why is that? Well, an example, a simple example to understand this is, let's assume the function, the correlation, this pi, this correlation function, let's assume it's like this. So m squared of p squared is approximately a constant, m squared, capital M squared, plus something linear in p squared, so alpha p squared. If I substitute this here, what do I do? Well, p squared now will be multiplied by 1 plus alpha, and then I'll have here m0 squared plus m squared. But then I have to divide by 1 plus alpha in order to have p squared in the denominator. So I write this as minus I times 1 plus alpha to the minus 1 divided by p squared plus m0 squared plus capital M squared over 1 plus alpha. So you see that in this case, I define this z, this wave function randomization factor, to be 1 plus alpha to the minus 1, and little m squared, the physical pole, to be m0 squared plus m squared over 1 plus alpha. Right? Of course, this was one example, but if there are higher order corrections to p squared, so in this case, I got an exact result. So I got exactly something of this form. But if I would introduce higher order corrections in p squared, so let's say p to the 4th, p to the 6th, and p to the 8th, and so on, then I can write this as an expansion in p squared. And then I will get this term plus from the expansion part, I'll get some finite terms. Right. So the moral is that this 1pi function, this polarization function, pi, or m squared of p squared, changes both the physical pole from this m0 squared to this combination, and it creates a wave function randomization z. All right. All right. So this is this is something that it's useful in order to calculate the physical pole, for instance, from by calculating the 1pi function. Well, I guess this is everything that I wanted to tell you. Yeah, that is everything. So do you have any questions? Well, somebody checked that they can still hear me. So if you can hear me, write something.
Yeah, you're hearing.
Okay, all right, good. So I guess that just means there are no questions, I suppose. All right, so then I'll see you next Monday. All right, bye.